In this video, we're going to talk about what is an appropriate sample size for a hypothesis test. And it really ties with the desired beta level or probability of type 2 error. Because when you look at formulas of beta, probability of type 2 error, you can see that it depends on these parameters. Sigma is the standard deviation of population that is known in advance. Alpha is probability of type 1 error, which typically is specified, but there is this relationship between alpha and beta. If you increase alpha, beta goes down and vice versa. So you can't increase alpha so much because it does good for beta, but it increases the type 1 error, so that's not good. But one of the parameters that you can play with and helps with your beta, minimizing your beta, is sample size, or n. Basically, if we choose one value of delta, which is difference between true population mean and your hypothesized mean, and specify a corresponding desired level of beta, let's say that your desired beta is 10% or 5%. Then we can choose an appropriate sample size that satisfies our desired beta level. For a two-sided hypothesis test, this is how you calculate n. For a one-sided hypothesis test, this is how you calculate n. And as you can see, it depends on your alpha, it depends on your beta. So beta really plays in this calculation of appropriate sample size. So let's take a look at one example, and this example was the GPA example, where we are hypothesizing whether the average GPA of the university is 3.0 or if it's not 3.0. And as you can see, it's a two-sided test, right? It is a two-sided hypothesis test. Now, given these piece of information like sigma and the testistat and alpha of the test, if we want beta of 0.01, this is your desired beta level, 1%, at mu of 3.2, and that is the true population mean. And that is something that is given. And in practice, you estimate that because it's hard to get. You don't have access to the entire population. It's an estimation. What sample size should we use? Well, because it's a two-sided test, looking at the previous slide, here is the formula to calculate n. So for part A, n is equal to z of alpha over 2 plus z of beta times sigma squared. So that is z of 0.025 plus z of 0.01 squared times 0.5 squared over 0.2 squared. And 0.2 is the delta. If this is mu, delta is mu minus mu naught, which is 3.2 minus 3.0. That is 0.2. So if you do the math here, these z values, z of 0.025, it is 1.96, z of 0.01 is 2.32, and you can read them from the z table. It is good to memorize these z values because they're very common. Okay, now you will get 115.02. Okay, but what do we do with that value? That is the appropriate sample size, 115.02. If you really want to satisfy the beta of your desired beta, you would have to at least have this sample size or more. If you increase the sample size, it's actually good. That will decrease your desired beta level. So what you need to do is to round this up. Round up this value and you suggest 116 as the required sample size. Now for part B and C, part B says if beta is the same beta and mu is different, now 3.25, what sample size should be used? So essentially, in this case, you're going to have a different delta, and that is 0.25. If your delta is now 0.25, and you follow this, and you follow the same calculations that we did for part A, n would be 73.2. Basically everything is the same here except this 0.2 squared becomes 0.25 squared. And then you have to round that up, that is 74. So we need smaller sample size compared to part A, because now we have a larger delta. And that makes sense. If the difference between what you're hypothesizing and what is truly happening in the population is more, then with a smaller sample size, you'll be able to identify that. Part C says if we want a beta of 0.05, so now we're basically loosening up our beta requirement. We're increasing beta requirement. And mu is 3.2, what sample size should be used? Well, essentially here the delta is 0.2, what we had in part A, but now we have a different beta. In the formula, this z of 0.01 changes to z of 0.05. So everything stays the same, just z of 0.05 is 1.64, and you basically use the same calculation. You replace that with 1.64, and you do the math with the same delta of 0.2. Your n would be 81. So 81 is the sample size that you would need to satisfy this beta level. If you increase your sample size, your beta goes down. It's a good thing. So this is important because choosing a sample size is critical. In a lot of applications, collecting data is not easy. And for example, for quality control applications, a lot of time collecting a big sample or collecting these samples are destructive. You would have to, destroy a part to measure that it's resistant toward a certain force. Okay, so it is important to only use the required sample size. That is the importance of calculating sample size.